Yesterday when we stopped, I think we are talking about this slide where we said that if you have an impulse signal and if you integrate, you get a step signal. And if you integrate a step signal, you get a ramp. And if you integrate a ramp, you get a parabolic. And conversely, if you have a parabolic, if you differentiate, you get a ramp. And if you differentiate a ramp, you get a step. And if you differentiate step, you get impulse. Okay, so this is where we stopped. Today, I would take you through initially Laplace transform of these simple signals. And we will look at first order systems, taking some examples. So first of all, as I was saying, you do Fourier transform when you want to convert partial differential equation into algebraic equations. So that way, Laplace transformation is very useful. If you have a function in time domain, let's say f of t, and you want to have the function in the frequency domain, that is S. So you do a Laplace transform of the function ft. And the mathematical representation of the Laplace transformation would be if you integrate the function ft into e to the power minus st dt from 0 to infinity. Okay, so that is basically how you do Laplace transform. So typically, if you look at this Laplace table, Laplace transformation table, for different functions in the time domain, you can have the corresponding function in the frequency domain, right? If you have ft, you can actually know what is fs. And similarly, if you have the function in a frequency domain, you can have the corresponding function in the time domain. So there are several functions that are listed here. If you look at a Laplace transform table, you will find these functions in time domain and correspondingly in the frequency domain. So here we are talking about these signals. So essentially you have the first one is impulse signal. Impulse signal is represented here. So you have the delta function, which is A only at time t equal to 0. And when time t is not 0, then the signal is basically 0. And if you take a Laplace transform of the impulse function, you actually get the same value, which is A. So the function has the same value both in time and frequency domain, because here it is at a particular instant. Okay, so the integration has no meaning because you are not talking about any finite time duration. So it's just the same value both in time and frequency domain. But if you go to a step function, typically you represent the step function as this. The function will be having some value, non-zero value a, when time t greater than or equal to 0. And it will have a value 0 when time is less than 0. Okay. So if you do a Laplace transform of this function, which is a is a constant. So basically you are doing Laplace transformation of 1. And if you go to this table, you can see that the Laplace transformation of 1 is basically 1 over s. Okay. So essentially you get a is a constant. So a you take out and then you do a Laplace transformation of only 1. So you get a by s. Okay. Similarly, if you go to a ramp function, so the ramp function is represented as you see here. T is a into t when t is greater than or equal to 0, and it is equal to 0 when it is time t is less than 0. So if you do a Laplace transform of the ramp function, so essentially you're doing the Laplace transformation of t, because a is a constant, it comes out of the transformation. So Laplace transform of t to the power n, if you see this table, Laplace transformation of t to the power n is basically n factorial divided by s to the power n plus 1. So in this particular case, it is t, so n is 1, so that should be 1 divided by s square. So that is what we get here. We get a divided by s square. Similarly, if you go to a parabolic signal, so parabolic signal is represented as a t square by 2 when time t is greater than or equal to 0, otherwise it's 0 elsewhere. So if you take a Laplace transform of this parabolic function, you actually get a, if you do a Laplace transform of t square by 2, you actually get 1 over s cube. So that is a over s cube. It is important to know how this signal would look like in a frequency domain going from a time domain. Now, we talk about the time response of a control system. Typically, in a control system, we have an input signal, and then we have the system function, which would typically have a gain and the time constant, which would work on this input and give some output. Okay. So the time response of any system would have basically two components. One will be the transient response. So let's say the system is, the output is at some value corresponding to some initial value of input, and suddenly you change the input to some other value, right? So the output will slowly change to reach to a steady state value. Okay. So before reaching the steady state value, you look at the transient response, and after it reaches steady state value, you actually look at the steady state response. So we talk about this example. Let's say initially your system is at some equilibrium and you change the input. Let's say you give a step input, and so initially the input is here, the output is also here. Let's say, the output is here, and the input is also here. Now suddenly you give a step input, okay, a non-zero step input. The question is how the output slowly changes to match to the input. Okay, so you see that there is a finite time that is required before the output can match to the input. So that is known as the transient response. So time from t equal to 0 to about t equal to 16 is basically the transient response. And once this response becomes steady and independent with time, you talk about steady state response. Okay. Not necessarily always the output will be equal to input. Okay. Output will be equal to input when your gain equal to 1. Okay. But depending on the gain, your output can be very different from the input. So what we know about the systems is that the transient response depends upon the system poles only. That means it actually depends on the time constant. Okay, pole meaning it is in frequency domain, but in time domain it is actually the time constant, and not on the type of input that you supply. Okay, so you can take any kind of input. Let's say you can take a step input, and you can analyze the transient response of a system. Okay, but the steady state response depends on the system dynamics, and therefore it actually depends on the input quantity. Okay, so the input quantity is different, the steady state output is different, but the transient response doesn't depend on the input. Okay, But if you want to know the steady state response, you need to analyze different signals. Depending on the test signal, your output is going to be different. So let's say we talk about a first order
Could you
system.
just go back to the previous slide, sir? I was just
Yeah.
noting the first point.
Yeah.
Thank you, sir.
Yeah, so I can actually share these slides with you. Okay, if what I will do is I will create a Google Drive, and because the slides I typically you may not find sufficient time to take notes. I can actually share with you a PDF copy of this slide.
That would be really helpful, sir. Thank you.
So I think, if I ask you, maybe typically the EndSem is open notes, so you can take printouts of these slides. Okay, I will do that. So this is a first order system which has only one pole, one time constant. So this is basically the output. CS is the output in the frequency domain. RS is the input in the frequency domain. And this factor here has K, which is typically the gain of the system, and the capital T, which is the time constant of the system. So as you see here, this is the input that is coming to the system, and you have the factor here, and you get the output. And depending on the value of the gain and the time constant, the output characteristics are going to change. So this time constant T is actually a measure of how quickly a first order system would respond to the input. Okay, so as the input changes, how quickly the output would respond to the input, that is characterized by time constant. The gain of the system is basically the ratio of the output to the input signal. Okay, so if the gain is high, then the output is going to be higher than the input, and if it is low, it will be lower than the input signal. Let's take this example of the first order system, which is given by this factor. G of S is 10 divided by 3S plus 1. Okay. As I said, always this system parameter is represented as K divided by 1 plus T into S. So if you bring analogy with this, your gain is basically 10 and 1 plus T into S. So time constant is basically 3 seconds. Okay. Now, if you take another system, which is represented as GS is 3 divided by S plus 5, how do you know the time constant, gain and time constant? So you have to bring it to this form, right? K divided by 1 plus TS. So if you do that, you have to actually take 5 out. So you get 1. And this becomes 1/5 of S, right? And if you divide the denominator with 5 to make the value remain the same, you also have to divide the numerator by 5. So the numerator becomes 3 by 5. So once you bring it to this form, K divided by 1 plus TS, you can actually find out what is the gain and what is the time constant. So the gain happens to be 3 by 5 and the time constant happens to be 1 by 5. Okay. So having understood that, let us now consider this first order system. Okay. So we have the first order system. RS is the input, as I said, and this is the system operation, and CS is the output. So you have gain and time constant. Now, if I have an impulse signal as the input, that means when time t equal to 0, I have some non-zero input, and the signal is 0 everywhere else, right? And I represent that in time domain here. So that is delta t equal to 1 when t equal to 0, and delta t is 0 for other values of t. Now, if I convert it to frequency domain, as we had seen in the beginning of today's class, the Laplace transform of a unit impulse signal is basically 1. Okay. So now your output would become, so your input in the frequency domain is 1. So your output will be just the system factor, which is k divided by 1 plus Ts. Okay. Now, if you rearrange this slightly, okay, if you take T common from the denominator and you rearrange this slightly, because you want to do it in a form that you can convert from this frequency domain to time domain. So that is why you have taken T common. So you have k by T in the numerator, and in the denominator you have S plus 1 by T. Okay. Now we have to know the frequency response in the response of the system in the time domain. Okay. So what we did, let me clarify. So to perform this system operation, your input is converted into frequency domain. Now your output is obtained in the frequency domain. Now to understand the characteristic, you convert this output that is in the frequency domain back to the time domain. Okay. Now, if you want to convert this output in the frequency domain to the time domain, you have to do something called inverse Laplace transformation. Okay. So basically, you have to find inverse Laplace of this function. Now, as I was telling you, if you go to this table, you have a function here which is something similar to 1 over s minus a. Okay. So you see here, this k by t is basically like a constant. Okay. Because k is a gain and t is the time constant. So this is a constant as far as time and frequency are concerned. So this is constant. 1 by t is also another constant. And then you have frequency. So basically this k by t, if you take out, you have 1 over s plus a. Okay. So this is similar to this form. Okay. Here you have minus a, but if it is 1 over s plus a, this will be the time, the inverse Laplace of this 1 over s minus a is basically e to the power at. So the Laplace inverse of 1 over s plus a will be e to the power minus at. Okay. So, and you have here in the form 1 over s plus a. 1 by t is your a. So basically, if you take Laplace inverse of this equation here, this expression here, you get, so k by t is a constant. So e to the power minus a into t, right? And your a is basically 1 over capital T. So minus 1 over capital T into t, which is e to the power minus small t over capital T. So this is in the time domain. So for an impulse input signal, your output in the time domain is going to look like this. That is the gain divided by the time constant e to the power minus t divided by the time constant. This is how the output is going to change with time with respect to for a impulse input. So this, if we represent pictorially, right? So this is basically the output, which is c as a function of t is k by t e to the minus t by t. Now we can take specific values of gain. Let's say in this case your gain is 3, k is 3. And let's call the time constant, let's take the time constant is 2 seconds. So we can actually plot this characteristic here. So in the x-axis you have time, and in the y-axis you have the output. Okay. So you can see that for a step input, quickly your output is going to be basically when t is 0, time t is 0, this is 1. So your output is basically k by t, that is 3 divided by 2, which is 1.5. And as time proceeds, it is going to decay following e to the power minus t by t. Okay. And you would see that for a first order system, this output is going to converge, decay, and become 0 because your impulse signal is only at t equal to 0. So as soon as you give a impulse signal, your output is matching the input and becoming k by t. Now there is no signal here, so your input is 0. So the output would have to come to 0, but they don't come down instantly like the input signal. The output signal decays following e to the power minus t by t, but finally it actually decays to 0. And for a first order system, typically it takes about 5 times the time constant to follow the input. That is, here your time constant is 2 seconds. So it decays to the input or the 0 in this case at about 10 seconds. So you can see that at 10 seconds, the output has reduced to the input, which is at 0. Now, so this was about if you give an impulse signal. Okay. What if you give a step signal? So if you have a step signal, so let us, so this is the typical first order system. So you have the input and you have the system factor, and then you have the output. Now, for a step response, we have seen that in the frequency domain, the step response is expressed as 1 over s, right? We had seen, if I take you to this slide, this is what we had gotten, right? The Laplace transform of the step input. In this case, it is a, so it is a by s, but if a is 1, then it will be 1 over s, right? So that is what we see here. Let's say our input is a unit step signal. So for an unit step signal, in the frequency domain, your input will simply be 1 over s. So your output would basically be the factor here, k divided by ts plus 1 into the input, which is 1 over s. Now, if you want to understand the system characteristics in the time domain, you have to do a Laplace inverse of this expression in the frequency domain. Now, in order to do that, you need to basically do some mathematical rearrangement. Okay, because you cannot get Laplace inverse of every function arranged in every manner. So you have to bring a given function, rearrange and express it to express in a certain way for which the inverse Laplace is available. Okay. So you need to, in this case, you need to break this into partial fraction. So for example, you can write Cs is k by s minus kt divided by ts plus 1. So if you do the math, it is basically same thing, but we have expressed it in a different way because we have the inverse Laplace of 1 over s. We also know the inverse Laplace of 1 over ts. That is why we have written this to this form. But they are the same thing, right? You can see if you take the LCM of s into ts plus 1, here you get k ts plus k, and here you get minus kts. So minus kts plus kts will cancel, and you will only get k divided by s into ts plus, same thing. So you want to understand the system characteristics in the time domain. So you take an inverse Laplace of this expression. So when you do that, you basically take inverse Laplace of 1 over s, which is basically the unit signal, which is if this were a, it will be a. If it is 1, it will be 1. And the Laplace inverse of t over ts plus 1, if you take t common from the denominator, which will get cancelled with this t, you will have s plus 1 over t. 1 over t is like a, right? So it will be e to the power minus at. So e to the power minus 1 over t into time. So this is basically in the time domain. Okay. How the output is going to vary with time when you expose the system to a unit step input. Okay, so basically this is what you have a unit step input. So this is how the output is going to vary when you have a unit step input. Now, if you want to know when my time is same as the time constant, okay, the time is same as the time constant, first time constant, 1 into t. Then what will be the output? So you can just simply put small t equal to capital T. So this will be k into 1 minus e to the power minus 1. So it is 0.632 into k. Okay. When small t is capital T. What does it mean? It means that let's say, we take an example where k is 10. That means the gain is 10 and time constant is 1.5 seconds. So here we said that when 1.5 seconds have elapsed, so that means your small t is 1.5 seconds, which is same as the time constant. What is the value of the output? So we see here that when our time is one time constant, your output is, if you just substitute here k equal to 10, this is basically 6.32, right? So your output is 6.32. Now, your gain is 10, okay? Your input is 1. So the output would basically be 10, okay? Because the gain is output, steady state output divided by input. So the steady state output will be 10. Now, at first one time constant, the output has reached nearly 63% of the steady state output. Okay, so this 0.632 into K says that the output has reached 63% of the steady state output. This way, if you go to 5 times time constant, so that is 7.5 seconds, you will see that it would have almost reached the 99%, more than 99% of the steady state output, which we'll talk about in a while from now. But this is how, see, this is the step input. It is at 1, okay? Your gain is 10. So this should be the steady state output. Now this is the transient response of the system. It increases following 1 minus e to the power minus t over t and attains steady state at some 5 times time constant. Okay, so this is a typical characteristic of first order systems. Okay. Now here you can see, right, different t. We said that at first time constant, the output at first time constant, the output would have reached about 63.2% of the input. Okay. Similarly, if you take twice the time constant, if you take your small t is 2t, then you would see that if you just come here and you put t equal to 2t, so you will have basically 1 minus e to the power minus 2 and k is 10, right? If you calculate that, you can show that it will come out to be 0.865. That is 86.5% of the output. So at 2 time constant, your output will reach 86.5% of the steady state output. Okay. Similarly, at 3t, it will reach about 95%. At 4t, it will reach about 98.2%. And as I was saying, at 5t, it would have reached nearly 99.3% of the steady state output. Okay. Which is taken as almost as the output because it is within plus minus 1%. And you say that your system response has actually reached the steady state output at 5 time constant. What does it mean for real application? It means that, let's say you are measuring temperature using a thermocouple. Okay. You are measuring some temperature, let's say, 40 degrees centigrade. Let's say your heat flux changed and your surface temperature changed to 45 degrees centigrade. So the temperature is going to change, but the consequence, what your thermocouple is going to measure is voltage, right? As output because of the Seebeck effect. Now the question is, how long should you wait before you actually record the data, right? So your system should have reached the steady state. That means if your time constant of the system is, let's say, 3 seconds, then you should reach something like 15 seconds before you actually record the temperature for a higher heat input. Okay. So it basically tells you how frequently you should record output when you have a change in the input. Okay. So in that way, the time constant is very important in practical measurements. Right. So I would basically move to another slide and talk about some examples of more examples of first order system. real examples. Let me just come back. Okay, so little bit more about the first order system. First order systems are very powerful, and they are, as I said, applicable to many different kinds of real world systems. And second thing is that these first order systems will have a common generic mathematical framework. That means I had shown you the governing equations last class for a typical first order system. The same mathematical equation would apply to all kinds of first order systems. Okay, so it has a fixed mathematical framework. If you understand one, the others you can analyze in a similar way. So here I will take examples from mechanical systems, electrical systems, thermal systems, and fluidic systems. And we talk about how we can analyze first order system. So the first system is a air piston damper. Okay, so this is an image of an air piston damper. So typically, this is basically a spring steel beam, and it is attached to a cylinder here. Sorry, the piston here. The piston is within the cylinder, and this piston basically moves up and down, and there is an orifice here. So when the piston moves down, the gas or air leaves this control volume, and when this piston moves off, air gas is sucked in. Okay, and this orifice, there will be some kind of a valve or a knob, and you can control the opening inside the knob to control how much air resistance or the gas resistance of the flow path when the air tries to move out or move in. Okay, so basically, because of this presence of this orifice of the valve, there is some damping also coming into the system here. So the system damping is because there is some resistance when the piston tries to move down. And because of this spring beam, you have some kind of spring constant in the system. So you have spring constant and you have damping coming into this system. So a simplest representation of this kind of system is called a spring dashpot system. So here, this is the fixed frame, and you have a spring, and here you have basically a dashpot, and these are attached to a link. Basically, the spring and the dashpot system mechanically are mechanically linked through this massless plate, you can say, right? And since it is massless, it will not impart any inertia force, right? There will be no inertial force contribution coming from this massless plate platform. And in this analysis, we assume that, let's say this massless platform can only move in the x direction, so there is no movement in the other direction. And when this tries to move, let's say it tries to move by a distance x in the positive direction, the spring force would act in the opposite direction. There would also be some damping coming from this damper. So this spring force is proportional to the displacement, right, which is x. So the spring force will be the spring constant k times x. Similarly, the damping force, the spring force is proportional to displacement, that is x. Whereas the damping force is proportional to the velocity. Okay. So the damping force Fb is basically the damping coefficient B times the velocity, which is in terms of displacement, it is dx over dt, right? So now if we do a force balance, okay, so you can, like for example, if you cut the system here, you see that, there will be spring force and the dashpot, the damping force coming in this direction on the spring and the dashpot. Similarly, on the massless link, it will be in the opposite direction, right? And so if you do a force balance, you can say that the spring force basically acts in the negative direction when it tries to, the displacement is in the positive direction. So as the damping force. So that is why this is in the negative Fk minus negative Fb, which is minus Kx minus B dx by dt equal to 0, because there is no inertial force. So this is right hand side is 0. So if you rearrange this, you basically get B by K, right? If you divide K, B by K into dx over dt plus x equal to 0. Now, this characteristic equation is similar to what we had, what I had shown you in the very first class when we started talking about first order system. The first order system typically is represented in this form: tau, which is the time constant, dy over dt plus y is 0, and y is basically can be displacement, temperature, anything. In this case, y is displacement, or here in this equation, x is displacement. So these two, if you compare, you can see that this B by K is similar to the time constant here. Okay. So in fact, in a spring dashpot system, the ratio of the damping coefficient to the spring constant gives you the time constant. Okay. Time constant is represented as B by K. Now, so you have a solution to this equation, right? Typically, it is e to the power minus t and tau. So you have essentially a solution to this equation in that form. And here, such a solution is written. So basically, your displacement is here. You can say that this is basically the coefficient, which is 1.5 into 10 to the power minus 2. Last class we had written, right? So solution to this equation will be C, some constant time, e to the power minus t by tau. So this is that C, and e to the power minus t by tau. So tau is basically 1 over 0.65, okay, and 1 over tau will be 1.65. Okay, so that is why 1 over tau is coming here as 1.65. And for a given dashpot, you can also find what is the value of B. So B is basically here. B is K into tau. So you can estimate B will be equal to K into tau, which is this. So this is a specific example. But what is important to understand is this characteristic curve here. Okay. So you can see that initially your what you do is basically you stretch this very slowly to some other position and slowly leave it. So according to first order system, this should slowly come back to its original position. So that is what it is doing. So initially you have, when t equal to 0, your displacement is 1.5 into 10 to the minus 2, which is shown here, 1.5 centimeter. And as time progresses, it is going to decay following this. And finally, it wants to come back to its original position, which is x your y equal to 0. And that happens over 5 times time constant. So here our time constant is about 0.61. So you can see that 5 times the time constant, which is close to 3 seconds, your output has come back to its original state, okay, which is 0 displacement. So this was for a mechanical system. We can also take yeah.
So one doubt.
Yeah.
How the value of K is 117 in the previous one?
So here we have basically taken an example where K is 170 and tau happens to be 0.61. So these are examples that we have taken. Okay, these are for a specific case. But for actual system, if they have given you the value of B or K, you can actually find tau. Okay, this is just an example.
Okay. We didn't take from the equation. It is
no. All you get from the equation is that whatever is given. Let's say your tau is given in this case. So you get 1 over tau and here. And if you take the C here, that is also given here. And if the K is given, you can find B. Okay, so these are all taken as examples.
Okay, sir. Thank you.
Okay, let me.
Professor Engg, I have a doubt. I'm sorry to just interrupt you. Suppose, sir, we are measuring a temperature of a surface, okay?
Yeah.
And you told that before you record the temperature, you should wait for time constant so that it will get settled out to a steady state, and then it will be giving the what I'm going to say exact value in that sense.
Yeah.
Now, for example, suppose I have a system in which I can vary temperature instantly. What I mean to say is I increase the heat flux so that temperature goes to 20 and then come back to, let's say, 5 degree. And if I want to measure every temperature at every instant, like T is equal to 0, T is equal to 1 second, 2 second, 3 second, 4 second, 5 second, how the temperature rose up to that level and come down to 5, then whether I have to and time constant of the system is around 5 seconds. That means that measurement technique we cannot use over here.
Yeah,
that
so
means
that is the thing. So yeah, that is why when you want to change your input instantly and you want to measure the output instantly, you have to use your temperature probe sensor, which should be good enough, which should be fast enough, right? So your time constant of the instrument has to be very, very small. Okay. So you are saying that you are going to change the input in every second, and you want to measure also every second. That means the time constant of the system should be very small, right? Maybe 10% of 1 second, maybe 0.1 second, or even small.
Right. Thank you.
So I will stop here. We are almost time, and but if you have any question, we can discuss.
Sir, the recording I'm not recording. Sorry, the slides you would be sharing us on the Google Drive.
Just give me 1 second. Give me 1 second.
Recording stopped.
Yeah. Yeah, please say.
Sir, the slides you would be sharing on the Google Drive, right?
Yes, yes. So what I will do is yesterday's class and today's class, I would try to put them in a Google Drive and share a link with you. In fact, from here on, I'll be teaching on slides, so I can share with you every week.
Okay, thank you, sir.
Sir, just to understand the nature of the course going forward, so how will we be studying the thermal measurements aspect of things when we, understand the fundamentals like first order system, second order system? Can you just give a brief idea?
So when we talk about the transient response of as I was telling you yesterday, when you want to study the transient response of temperature systems, and their knowledge of this first order system is going to be useful. Okay, let's say I take an example of the response of a U-tube manometer subjected to a pressure change, right? So when there is a pressure change, and if you want to know, okay, how quickly your manometer can measure the new pressure, so their knowledge of second order system is going to be important. Okay, so but this is something is going to come. So for now, I think you should try to learn the behavior of this first order and second order system, but you will actually understand it better and you realize when you actually cover the course. Okay.
Thank you, sir. Yeah.
In fact, knowledge of first order, second order system goes beyond what we cover in this course. As I said, you may not be able to cover electrical system, but there are many electrical systems which are first order, and there are many electrical systems which are second order. So if you want to understand behavior of the system, knowledge of these is going to be useful. Okay. So your RC circuit is typically a first order system. If you take RLC, it becomes a second order system. So, if you want to analyze those systems, then knowledge of order of system becomes critical.
So are there any systems about second order, sir?
So as I said, there will be higher order systems, but the thing is the math becomes so complex that we typically decompose higher order systems into first order and second order system and apply the mathematics coming from only first and second order systems.
Sir,
Actually, first order, second order systems are approximations. So if you do not, make suitable assumptions, then these are higher order systems. So you cannot really mathematically resolve them to understand. So
can we say that the autonomous vehicles and all those things come under the higher order systems?
all real systems are higher order systems. Like this example that we took, right, of a spring mass system.
Yes.
And let's say we say it is linear displacement, x-axis, but if it moves x and y, you cannot analyze using first order system. It's a higher order system. And if there is acceleration in the system, it is a variable acceleration system. I mean, it becomes incredibly complex. And so all real systems are higher order system. And how good is the approximation is that something you need to see.
Okay, sir.
Sir.
Yeah.
Yes, sir. Sir, you said that means a higher order system becomes complex to solve, so it is means broken into first or second order system and then we solve it. So when it comes to mathematical solver like MATLAB and other programs, so those work in higher order system itself, or those systems also break it into first and second order system and then solve it? How that
Yeah, so
works, sir?
typically you will not get any physical insight. See, if you take a real system, but you have to represent the governing equations for the real system, right?
Yes, sir.
So typically the governing equations are approximations.
Yes, sir.
So even if you know that it is a higher order system, your governing equations may not be adequate to fully represent those systems, right? So let's say your displacement is, your equations come to be like y to the power 4, y to the power q, y square, and all that. And your coefficients are also varying with time and space. Even very complicated, very advanced computing power you may have, but how do you mathematically represent those behavior to be able to solve it? Okay. What is boundary conditions? How do you get the boundary conditions? There may not be enough boundary condition to resolve those equations. So there are practical implications, although computing resources can be infinite, but you must have, finally, you are going to tell the computer that these are the conditions based on which you need to solve these equations, right? So you may not have enough condition also. Okay.
Understood, sir.
So can you please share the slides which you've taken?
Yes, I mean, may not be today, but tomorrow morning I would share for this week. Yesterday.
Okay, sir.
Okay.
Sure.
All right. So if no further question, then thank you, and we will meet again Monday coming week.
Thank you, sir.
Thank you, sir.
Thank you
so
very
much,
much, sir.
sir.
Happy.
Thank you, sir. Thank you, sir.